Hello and welcome to my presentation on my AP Computer Science project. For my project, I decided to explore fractals, which are geometric shapes or images that repeat itself over and over again. The first fractal that I did is the Sierpinski's triangle, which is a very famous fractal that you've probably seen before. It's basically a triangle, but an upside down equilateral triangle is placed in it over and over again on the three outer equilateral triangles. In my fractal, you can divide the outer triangles over and over again, and you can see the different stages of the Sierpinski's triangle. There are a few mathematical properties of this Sierpinski's triangle, one of which is that in the Pascal's triangle, which is basically a triangle where the number is the sum of the higher two numbers, all the even numbers are in the pattern of the Sierpinski's triangle. Because an even number is only there when there are two odd numbers beside each other, and the sum of two even numbers is another even number, which gives this triangle this shape. The next fractal that I'm going to introduce is a tree fractal. Now, we've all seen trees before in our everyday lives, but we've probably never thought of a tree as a fractal. But this looks like a tree, but it is actually a fractal. After every branch, it branches out into two separate branches. In this, you can manipulate the tree so that the angle it branches out changes, creating beautiful geometric shapes. Here is the tree as the angle increases. As you can see, it's beautiful. It stops looking like a tree after it goes down, but it's still the same thing over and over again. And in nature, trees are just like that. It's the branches branch out, and then more branches branch out from the branches, which is why fractals are more common than we think they are, and not just something that appears on screen. Like, as you can see, this looks like a pretty realistic tree. The next fractal I have is a seashell. It's not actually a seashell, and it was a bit of a mistake. I was trying to make the tree when I came across this, and I decided that I couldn't bring myself to delete it because it's too pretty. Let's see it again. So basically, it's just a line but bent at an angle as it goes along, and it's drawing things as it's bending. So basically, when the angle is lowered, there's more bends before, while there's the same amount of bends, but since the angle, for example, up here is so large, it looks almost straight, but down here the angle is small, so the same amount of bends can cause this curving thing to happen. The next, and probably my most favorite fractal, is a fractal that doesn't look like much at the start, but it has amazing mathematical properties. So basically, you start with a white square, you put another white square beside it, and every single time you take the same picture and you flip it counterclockwise by 90 degrees. Think for a moment of how it like flips and becomes this beautiful fractal. Now, this might seem like nothing much, but there's a lot of mathematical properties of this fractal. For example, would you believe me if I said the slope of this line is exactly this? The slope of this line right here approaches the golden ratio as this fractal goes on, or that the area of the number of white squares, which is the area of the white below this line, is exactly half of the area of the line above this line, as the fractal approaches infinity. It might not look like it's true, but it is. So my first claim is true because of this. And also notice that like the fractal is upside down because the Java coordinate plane system starts from the top left corner instead of the bottom left corner. So if a line slopes up, it's supposed to go down. It goes down in my interpretation of the fractal and etc. So here is why the slope of this fractal approaches the golden ratio, or phi. Slope is y over x. So the slope of this line is, in this diagram, is b over a using the coordinate system because this line has length a and this line has length b. But the slope is also a over a plus b because this has length a and this has length a plus b. So cross multiplying this, we get b times, in parentheses, a plus b equals a squared. So b squared plus ba minus a squared equals 0. Dividing by 8 squared, we get b over a squared plus b over a minus 1 equals 0. And using the quadratics formula, b over a equals -1 plus or minus root 1 plus 4 over 2, which equals to -1 plus or minus root 5 over 2. It has to be positive because the line is sloped upwards, so the slope of my fractal is -1 plus root 5 over 2, which is the golden ratio. So as I was making phi1, phi is the Greek letter that represents the golden ratio, I accidentally made phi2 and it was too pretty to delete. Basically, it's the same thing, but instead of just flipping counterclockwise, you flip counterclockwise and then flip it and then reflect it across the vertical axis. So it looks like this. You flip 90 degrees counterclockwise and reflect it across the vertical axis and then puzzle it on next. As you can see, this is also very pretty. The slope of this line is still the golden ratio, but unlike the previous one, it's just the line and a thing that sort of looks like a flag. And another pretty thing about this is, if you look at this right here and you move it physically over here, it looks the exact same. And this part right here, if you flip it, and then it's the same as this. So basically all of these are the same shape over and over again, which is cool. And the special thing about this is this pretty fractal is completely original and like I came up with it. So this is my AP Computer Science project. I hope you enjoyed. Thanks for watching.